There exists somewhere in the cold reaches of space, right now, a wanderer that has been traveling toward us for thousands of years, without hurrying, without intention, pulled only by the patient gravity of our sun. You cannot see it yet, but it is coming. And when it arrives, it will arrive gently. Its arrival written into the mathematics of orbital mechanics, with the same precision that governed its departure from the outer darkness so very long ago. Imagine standing beneath an open sky, on a night so clear that the air itself seems thin enough to touch the stars. The temperature has dropped to that particular coldness where breath becomes visible, where sound itself feels muted by the still air around you. Above the horizon, somewhere between the familiar constellations, there is a faint smudge of light. Not a star. Stars are sharp and definite and fixed. This light is softer, more diffuse, drifting almost imperceptibly across the darkness, as though the night sky itself has learned to move. This is not an airplane, not a satellite, not any human object launched from Earth. This is something far older, something that has been wandering the solar system since before human civilization had a name for itself. This is a comet. Why should a comet relax you? Perhaps because it represents the ultimate expression of patience. A comet does not rush. It does not deviate from its path out of anxiety or urgency. It has been following the same gravitational trajectory for millennia, and it will continue following that trajectory for millennia to come, indifferent to our worry, indifferent to our sense of time. There is something profoundly soothing about contemplating an object so vast, so ancient, so utterly unconcerned with the brief flutter of human existence below it. The faint smudge above your horizon is a frozen wanderer, a nucleus of ice and ancient dust and primordial rock, perhaps no more than a few kilometers across, yet somehow visible across the immense gulf of space. It is a fragment of the solar system's earliest moments, preserved in ice and stillness, carrying within itself materials that predate not only human civilization, but the Earth itself. Around that frozen nucleus streams a vast cloud of evaporated gas and dust, illuminated by the distant sun, creating that gentle luminescence that first drew human eyes skyward thousands of years ago. Behind the comet, two tails stretch backward into space, one of dust, golden and diffuse, and one of ionized gas, sometimes tinged with blue, both flowing away from the sun in the solar wind like the gentlest of cosmic breezes. If you have ever found yourself drawn to the night sky, if you have ever stood in the darkness and felt the weight of cosmic time settle over you like a blanket, then you know the particular peace that comes from contemplating objects so far removed from human concerns. Comets embody that peace. They have been wandering for longer than our species has existed. They will continue wandering long after we are gone. If the slow, ancient stories of these cosmic travelers speak to you, if you find yourself curious about the deeper details of how our solar system came to birth such patient wanderers, consider subscribing for more slow-paced, science-rich explorations of the relaxing facts about comets, journeys through the quiet corners of space where ancient light still carries stories billions of years old, where the vastness itself becomes a form of comfort. The night is cold and still. The comet, invisible now in the daylight, continues its long approach. Somewhere in the darkness, mathematics and gravity write a story that will not be rushed, that requires no explanation beyond its own existence. That story begins in the beginning, 4.5 billion years ago, in a place that was not yet our solar system, but rather a vast cloud of gas and dust and primordial material, spinning slowly in the darkness of the early universe. Picture that ancient nebula, not empty space as we might imagine it, but a vast, diffuse cloud of hydrogen and helium and the heavier elements forged in the hearts of dying stars. This cloud had no center yet, no organization. It was simply matter, drifting in the darkness, following the gentle pull of its own gravity. But gravity, patient and relentless, was already at work. The cloud began to contract, slowly at first, then with increasing momentum as material drew closer to material, as density increased, as the slow dance of cosmic assembly began in earnest. As the cloud contracted, it began to spin, not because anything set it in motion, but because all motion in the universe is relative, and as the cloud pulled together, any slight rotation became more pronounced. You have seen this principle before, perhaps without thinking of it in these terms. A figure skater, spinning slowly with arms outstretched, spins faster as the arms are pulled inward. The cloud worked in the same way, though on a scale almost impossible to comprehend. As it contracted, it rotated faster, and as it rotated, it flattened into a disk, our solar nebula, the birthplace of everything we know. Within that disk, temperature and pressure varied dramatically. At the center, material grew so dense, so hot, that nuclear fusion ignited, and the sun was born, a star, patient and reliable, burning steadily outward in all directions. But the disk surrounding the sun remained cool, especially at its outer edges, and in that cooler region, at distances we might measure in billions of kilometers from the young sun, something remarkable began to happen. Water ice, frozen solid in the deep cold of space, began to condense. Dust and rock particles began to adhere to one another, building larger and larger aggregates. Carbon compounds, the chemical basis of life itself, began to accumulate. Methane ice formed. Ammonia ice formed. The primordial solar system was slowly, patiently assembling itself from the most basic materials, and in the outer reaches, in the cold darkness beyond where any terrestrial planet would eventually form, the seeds of comets were being sown. What we are observing, in those rare moments when a comet becomes visible to our eyes, is essentially a time capsule, a frozen wanderer, composed of materials so old that they predate the existence of our Earth itself. At its most fundamental essence, a comet is an accumulation of ice, water ice, frozen carbon dioxide, frozen methane and ammonia, all bound together with ancient dust and rocky fragments, held in a loose gravitational embrace that has persisted for longer than human civilization has existed. Imagine, for a moment, a cosmic snowball tumbling through the void. Not pristine, not smooth. This snowball is dark, darkened by carbon-rich dust that has collected upon its surface across billions of years. Embedded within that ice are silicate particles, grains of rock so fine they would pass between your fingers like powder. There are also organic molecules trapped within the ice, complex chains of carbon and hydrogen, the very chemistry that we associate with life itself, though in these frozen wanderers they exist in a profound stillness, inactive, waiting. The nucleus of a comet, the solid core that gives it its identity, is remarkably small. We sometimes imagine them as enormous, catastrophic objects hurtling toward the sun, but in reality, most comets have nuclei measuring only a few kilometers across. Some are barely a single kilometer from end to end. Yet despite their modest size, they contain within them the memory of the solar system's infancy. These fragments are leftovers. They are the material that did not coalesce into planets, that did not fall into the sun, that instead drifted outward into the cold, quiet regions where time moves differently. This composition, ice and dust and ancient stone, means that a comet is fundamentally fragile, delicate even. When a comet ventures close to the sun, as we shall explore further, these materials begin to sublime, to transform directly from solid ice into vapor. The outer layers of the nucleus begin to evaporate, releasing gases and dust into space, and it is this release of material that creates what we observe as the comet's distinctive coma and tail. But in the vast stretches of time when a comet dwells far from the sun, it remains unchanged, frozen, waiting. There is something profoundly calming in understanding this. A comet's existence spans incomprehensible durations. It may spend thousands of years, or hundreds of thousands of years, traveling through space where the temperature hovers near absolute zero, where no energy touches it, where it exists in a state of such profound preservation that scientists can study one today and learn directly about the conditions that existed when your sun was born. The comet does not worry. It does not decay in any meaningful sense. It simply persists. If you were to travel to one of these icy nuclei, and you would need to imagine this journey, for it would take technologies still beyond our reach, what you would find is a surface unlike any landscape on Earth. Not smooth, not symmetrical. Instead, a terrain scarred and shaped by countless impacts with smaller particles across eons, cliffs and valleys, ridges and depressions, all of it encased in ice that has the consistency of rock-hard permafrost, dark from the accumulation of organic compounds, cold beyond the range of human survival. The structure of a comet's nucleus is itself a puzzle that scientists continue to refine our understanding of. It was long believed that these nuclei were solid, monolithic bodies, but more recent observations suggest something different, something more interesting. Many cometary nuclei may be what we call contact binaries, or perhaps even rubble piles. Two bodies orbiting each other so closely that they appear as one, or loosely aggregated collections of smaller chunks held together by weak gravity and the freezing of ices. In other words, a comet may be less like a solid stone and more like a delicate sculpture of frozen material barely maintaining its form. This speaks to something essential about comets. They are not eternal in their current form. They are not unchanging monuments. They are ephemeral in the grandest sense, temporary, subject to forces that will eventually scatter them, evaporate them, or fling them beyond the reach of our sun forever. And yet they have survived, in some form, for billions of years. Does that not suggest a kind of resilience hidden within apparent fragility? A persistence that requires no effort, no activity, no struggle, merely the simple fact of existence in the cold. The ancient materials that compose a comet nucleus are, in a very real sense, the oldest objects in our solar system, older than the moon, older than the continents beneath your feet. In holding a comet in our understanding, we are contemplating objects that crystallized in stellar nurseries before our sun had even fully ignited. The ice froze, the dust settled, and there they remained, waiting, as if time itself meant nothing to them. There is something peculiar about following a single wanderer across the void for thousands of years, watching its slow migration through the dark, knowing that the same cosmic body your ancestors saw, burning across their night sky, might return to yours. And perhaps you find yourself wondering, as you listen to these ancient patterns unfold, whether there might be more to discover about these icy travelers, more stories hidden in the silence between their orbits, more science woven quietly into their tales. If you do, if the thought of returning again and again to these slow journeys through the cold corners of our solar system appeals to you, consider subscribing. What you'll find here are long, thoughtful explorations of comets and their ancient light, narratives designed to move at the pace of contemplation rather than urgency, each episode unfolding like watching a comet trace its path across the hours of a long night. These are science-rich stretches through territory most of us only glimpse, told in a way that honors both accuracy and wonder, that treats the history of human observation and discovery as something meditative rather than rushed. The universe keeps its deepest truths for those patient enough to follow them, and comets especially reward that patience. They move through our awareness the way sleep itself moves through consciousness, gradually, gently, always returning to the same quiet place. Subscribing means you'll never miss these slow drifts through space, these careful reconstructions of how humanity came to understand these frozen wanderers and what they reveal about our own origins. And so we turn now toward the very beginning, toward the moment when the first comets were born, when the solar system itself was still taking shape in the cold and darkness of deep time. 4.5 billion years ago, long before Earth had cooled enough to hold the first drops of liquid water, long before the moon hung in our sky casting back the sun's light, there existed something far older than memory, far more patient than any living thing we have ever known. A vast, slowly spinning cloud of dust and gas, collapsing inward under its own immense gravity. This was the solar nebula, our sun's nursery, and within it, specifically at its outermost, coldest reaches, where the temperature dropped so low that even volatile molecules froze solid, the very first comets began to gather. Imagine, if you will, the sheer scale of this early solar system. The inner regions, closer to where our sun's heat began to ignite, were warm enough that lighter, more volatile elements drifted away as vapor. But farther out, in those cold and distant reaches beyond what would eventually become Jupiter's orbit, something remarkable happened. Water froze, methane crystallized, carbon dioxide, ammonia, and countless other ices accumulated like snowflakes, settling onto an endless, dark landscape. Mixed among these frozen volatiles were dust grains, tiny silicate particles, some no larger than a grain of sand, yet each one containing elements forged in the hearts of dying stars. Iron, nickel, carbon, oxygen, the ancient building blocks themselves, now gathering together in the profound cold. What we call comets today are essentially the leftovers of this primordial assembly. They did not form all at once, nor did they assemble themselves into the sharp, distinct objects we might imagine. Rather, they accumulated gradually, almost gently, as countless smaller particles collided in the sparse environment of the outer solar nebula. One grain drifted into another. That combined piece attracted a third. Slowly, imperceptibly, over hundreds of thousands of years, these accumulations grew. Gravity, patient gravity, did most of the work, pulling these fragments together into larger and larger bodies. Some grew to be merely kilometers across. Others expanded into objects tens of kilometers in diameter. But all of them, regardless of size, shared the same essential composition: frozen water and other ices, bound together with rocky dust and ancient silicate grains, all compressed by their own modest gravity into solid, cohesive bodies. The remarkable thing about this process is its slowness, its gentleness. There were no violent collisions in the traditional sense during formation. Velocities in the outer nebula were extraordinarily low, perhaps just a few meters per second, when two bodies finally met. Even when objects collided, they did not shatter explosively. Instead, they stuck together, accreting material like rolling snowballs, slowly gathering snow on a winter's day. Each impact, each joining, added a little more mass, a little more gravity, making the young comet incrementally better at capturing additional material. And as this process unfolded across the outer solar system, countless comets accumulated, hundreds of billions, perhaps even trillions, if current models are correct. They populated a region we now call the primordial comet disk, an extended zone stretching far beyond where Jupiter would eventually settle. Each comet was a small, silent world, a frozen archive of the solar system's birth, composed of the very materials that had condensed from the collapsing nebula itself. They were so ancient that they contained isotopes and chemical signatures that had essentially remained unchanged since the solar system's formation. In a very real sense, each comet was a time capsule, a preserved sample of what the solar system looked like before planets, before moons, before the violent gravitational interactions that would reshape everything. The temperature in these distant regions was so profoundly cold that it seemed almost incomprehensible to imagine it. Not merely cold in the way we might experience a winter night on Earth, but cold in an almost absolute sense, approaching absolute zero in those cases where comets eventually drifted farthest from the sun's warmth. At such temperatures, the very concept of change becomes almost meaningless. Chemical reactions slowed to a crawl. Comets did not evolve or transform in any significant way. They simply persisted, silent and still, waiting in the darkness. And yet, within this absolute stillness, these frozen wanderers possessed something remarkable. Locked within their icy interiors were organic molecules, complex carbon-based compounds formed through simple chemistry driven by radiation and the cosmic rays that permeated the early solar system. Some scientists have detected within modern comets compounds like amino acids and other building blocks of life. This suggests, quite fascinatingly, that from the very moment comets crystallized in the cold outer nebula, they were already carrying within them the chemical alphabet from which living things would eventually be written. We do not know if this connection is causal, if comets would ultimately prove instrumental in seeding life on Earth, but the possibility exists, woven into the very fabric of their ancient composition. And so there they remained, for millions of years while the sun continued its gradual ignition, while the inner solar system's remaining gas and dust coalesced into the terrestrial planets, while Jupiter carved out its gravitational domain and began to clear away nearby debris. The young comets of the outer nebula simply waited, drifting in the cold, accumulating. They were among the most ancient objects that would ever exist in our solar system, and though they did not yet know it, though of course they could not know anything, their patient vigil was about to be disrupted by the gravitational dance of the planets themselves. And in that vast expanse beyond the orbits of Neptune and Pluto, where the sun's light arrives as merely the brightest of stars rather than a warming presence, there exists what we might think of as the sleeping quarters of the solar system itself. Two distinct regions, both almost incomprehensibly large, both nearly silent and still, contain the vast majority of the comets that have ever formed. These are the Kuiper Belt and the Oort cloud, and they exist in a state of such profound quietness that it can be difficult for our earthbound minds to truly comprehend the timescales involved. The Kuiper Belt is the closer of the two, extending from roughly the orbit of Neptune, about 30 astronomical units from the Sun, where 1 astronomical unit is the distance from Earth to the Sun, outward to perhaps 50 or even 100 times that distance. Within this vast disc-shaped region, countless small icy bodies drift in their ancient orbits, moving with a slowness that would make the slowest glacier seem frantic by comparison. These are the short-period comets, as astronomers call them, the ones that have already had their orbits nudged into paths that bring them back toward the inner solar system within periods of a few hundred years or sometimes thousands. But most of the trillions upon trillions of objects that populate the Kuiper Belt, remain locked in their current trajectories, drifting alone through the profound darkness, never destined to feel the sun's warming touch. What draws the imagination most gently, perhaps, is the sheer solitude of these worlds. Imagine a comet, a mountain of ancient ice and dust and primordial rock, floating in absolute darkness with no other object visible to its senses were it to possess them. The nearest neighboring comet might be millions or even billions of kilometers away. The sun, so distant now, casts barely enough light to read by. The comet simply moves, very slowly, through its predestined orbital path, completing a single revolution around the sun every few 100,000 years or more. This is not a state of excitement or change. This is rest on a cosmic scale. But the Kuiper Belt, vast as it is, represents only the inner suburb of the great comet reservoirs. Beyond it, beginning somewhere around 1,000 astronomical units from the sun, and perhaps extending as far as 100,000 times that distance, nearly a quarter of the way to the nearest star, lies the Oort cloud. This is where the true cathedral of comets unfolds, a spherical shell of icy bodies so enormous that it dwarfs the entire Kuiper belt like a grain of sand compared to a beach. Within this cloud, astronomers estimate, there may exist somewhere between 1 and 100 trillion cometary nuclei. That is not an exaggeration. We are speaking of something so vast that language itself begins to feel inadequate. The Oort cloud is named after the Dutch astronomer Jan Oort, who in the 1950s proposed its existence not because anyone had seen it. It is far too distant and far too dark to observe directly, but because he could calculate its necessity. When astronomers traced the orbits of comets that arrived unexpectedly from random directions, coming from no particular plane or pattern, they realized that these long-period comets must be stored somewhere in some great spherical halo surrounding the solar system. The mathematics required such a place. The observations demanded it. Here in this cloud, in the profound darkness at the edge of our sun's gravitational influence, comets drift with a patience that seems almost meditative. A single orbit through the Oort cloud takes millions upon millions of years. An individual comet might complete merely 1 or 2 full revolutions around the sun since the dawn of human civilization. It is a pace of motion so slow that we might, in our impatience, call it stillness. The comets are cold beyond any familiar cold, existing in a state of equilibrium with the nearly absolute zero temperature of deep space. They do not deteriorate, they do not change, they simply wait. What is it about these waiting places that speaks so deeply to something within us? Perhaps it is the recognition that somewhere in the cosmos, right now, trillions of objects are suspended in a kind of endless patience, moving through the darkness according to rules established billions of years ago, never hurrying, never straying, maintaining their slow trajectories as surely as a sleeper maintains their rest. The comets of the Oort cloud and the Kuiper belt do not age in any meaningful sense. They do not suffer the passage of time as we understand suffering. They simply exist, in the cold and the dark, moving in the deep certainty of gravity. It is difficult to convey, in language meant for waking minds, just how empty these regions truly are. If you were somehow to place yourself in the Oort cloud, positioned beside a comet, you would find yourself in darkness so complete that the stars overhead, though bright, would seem almost diminished. No sun would warm you, no other object would move nearby. There would be only the comet beside you, your own slow drift through space, and the vast patience of geometry. And yet, even in this profound stillness, nothing is truly motionless. Every comet continues its slow orbit. Every object maintains its ancient momentum. The universe, even in its quietest corners, is a place of ordered motion. The Oort cloud and Kuiper belt are not warehouses where comets are stored and forgotten. They are birthing grounds and waiting rooms, vast silent nurseries where the ancient bodies of the solar system drift through eons, occasionally disturbed by the gentlest of forces, sometimes nudged from their sleeping paths to begin their long journeys toward the sun. For billions of years, these frozen wanderers remain nearly still, suspended in the profound silence of the outer solar system. And yet stillness, as it often is in the cosmos, proves to be deceptive. Hidden beneath that apparent peace lies an extraordinary sensitivity to the gentlest of forces, forces so delicate, so infinitesimally small, that they move across millions of years like a breath of wind across still water. Imagine, if you will, the vast gravitational field that surrounds our sun, extending outward in all directions, weakening gradually, but never quite vanishing entirely. Within that field, trillions of comets drift. Most will drift forever, their orbits so distant, so removed from the sun's immediate influence, that nothing will ever trouble them. But every so often, and here is where the quieter dramas of the cosmos unfold, a neighboring star passes relatively close to our solar system. Perhaps not close in human terms, perhaps the star remains at a distance of several light years, a gap so immense that it would take thousands of human lifetimes to traverse. Yet in the scale of the Oort cloud, which stretches nearly halfway to the nearest star, such a distance is intimate. The gravitational pull of this distant visitor, however slight, however subtle, can perturb the orbit of a comet, can nudge it, ever so gently, toward a different trajectory. And so begins the journey. A comet that has rested in equilibrium for 4 billion years feels this imperceptible tug. Its orbit, previously stable, becomes slightly elliptical. It begins, infinitesimally at first, to accelerate. The pull of our sun, patient, constant, always present, gradually overcomes the inertia that has held this wanderer in place since the solar system's infancy. The comet's fall toward the inner solar system is not dramatic. It is not violent or sudden. Rather, it is a process that unfolds across millennia. Thousands upon thousands of years pass as the comet spirals inward, each orbit bringing it fractionally closer to warmth and light. The mechanisms that trigger these cosmic disturbances are as gentle as they are varied. A passing star, drawn briefly close to our sun by the large-scale dynamics of our galactic neighborhood, may exert just enough gravitational influence to destabilize the Oort cloud's outermost inhabitants. But the disturbance need not originate from outside our solar system. The massive planets themselves, Jupiter with its enormous gravity, Saturn, Neptune, and even Uranus, occasionally interact with comets in the inner Oort cloud and the Kuiper belt. A comet may gradually drift closer to Neptune, for instance. Neptune's gravitational field, acting over millions of years, can alter the comet's path so fundamentally that it begins what might be called a fall, a slow, patient descent toward the sun. What is remarkable about this process is its timescale. When we speak of a comet being nudged, we are not describing an event that occurs over days or years or even centuries. We are describing a metamorphosis that may require 1,000,000 years or several million years to complete. The gravitational perturbation itself might take place instantaneously. The star passes, the tug occurs, the comet's trajectory is forever altered. But the consequence of that tug, the actual inward spiral, unfolds across an epoch. In human terms, this is unfathomable. In cosmic terms, this is a gentle waltz. During this long fall, the comet remains cold and inert. It continues to be composed of the same frozen water ice, methane ice, and ancient dust that has defined it since its birth. It continues to be, to all external appearances, utterly unremarkable. There is no light emanating from it. No one watching from Earth during these millions of years would have any awareness that this particular wanderer had begun its journey. The comet simply continues to exist, following its new orbital path with the same mathematical precision that governs all celestial motion. And yet something profound is occurring. A threshold is being crossed, slowly and silently. The comet, for the first time in billions of years, is beginning to approach the region of the solar system where our sun's warmth holds sway, where radiation is no longer an abstract concept, but a tangible, growing force. That gradual increase in solar energy will, eventually, trigger the most visible and most beautiful transformation any comet will ever undergo. But that moment remains distant still. For now, the comet falls inward, patient and unchanged, a messenger from the ancient past, carrying secrets written in ice and dust across the darkness between the stars. When a comet draws near enough to the sun that its ancient ice begins to warm, something quietly miraculous unfolds. The structure of a comet, what astronomers call its anatomy, reveals itself as a layered system of profound simplicity, each part shaped by forces that have been at work for billions of years. At the very heart lies the nucleus, and this is where the true comet lives. The nucleus is perhaps smaller than you might imagine. Most are between 1 and 20 kilometers across, though some rare giants stretch further still. It is essentially a frozen conglomerate, a loose collection of primordial ice, water ice mostly, but also frozen methane, ammonia, and carbon dioxide, all bound together with dust and rocky debris, porous and dark, darker than charcoal. This nucleus rotates slowly as it falls toward the sun, and within its frozen interior lie the chemical fingerprints of the solar system's infancy. As solar radiation warms the outer layers of the nucleus, something begins to change. The ices transform directly from solid to vapor without passing through liquid, a process called sublimation, and this releases the dust and gas trapped within. This is where the comet's visible structure begins to emerge. Surrounding the nucleus, growing larger as the comet approaches the sun, is an envelope of material called the coma. The coma is an atmosphere of dust and gas, sometimes stretching to hundreds of thousands of kilometers across, far larger than the solid nucleus itself. Within the coma, molecules of water vapor, carbon dioxide, and other volatiles drift in a vast glowing halo. This coma catches and scatters sunlight, which is why we see the comet as a fuzzy, luminous object rather than a sharp point of light. It is a beautiful consequence of outgassing, of a world slowly releasing its volatile secrets into the vacuum of space. But the coma alone does not account for the comet's most iconic feature. Beyond the coma stretch the tails, and this is where the comet becomes most visually extraordinary, most alien in its grace. A comet does not have one tail, but two, and they are formed by fundamentally different processes, pushed outward by distinct forces. The first is the dust tail. As sunlight warms the nucleus and the coma, particles of dust, tiny grains of silicate perhaps, or carbon compounds, are released along with the gas. These dust grains, once liberated, are pushed outward by radiation pressure, the gentle but persistent pressure of photons striking the dust and imparting momentum. The dust tail tends to be broad and curving, often somewhat yellowish or brownish in color because it reflects sunlight. It can stretch for millions of kilometers, sometimes reaching across a tenth of the sky as viewed from Earth. Dust tails often curve because dust particles, once pushed outward by radiation pressure, continue to orbit the sun even as they drift away from the coma. Their trajectories lag slightly behind the comet's path, creating that characteristic curved shape, like a cosmic wake. The second tail is far more delicate and ethereal. It is the ion tail, composed not of dust, but of electrically charged gas, plasma, water molecules, carbon dioxide molecules, and other volatiles are ionized by ultraviolet light from the sun, losing electrons and becoming charged particles. These ions interact with the solar wind, that ceaseless stream of charged particles flowing outward from the sun. The solar wind sweeps the ions away from the comet with astonishing efficiency, pushing them directly away from the sun, always. This is why ion tails point almost perfectly away from the sun, regardless of the comet's direction of motion. An ion tail is typically narrower and more linear than a dust tail, often appearing blue or greenish in photographs because of the characteristic emission of ionized water and other molecules. The ion tail can extend even further than the dust tail, sometimes stretching beyond 20 million kilometers into space. Together, these two tails create the comet's distinctive anatomy as it approaches the sun. The nucleus remains unchanged, a silent core of ancient ice, while around it blooms this temporary, magnificent structure. The coma swells, the tails expand and curve and stream, shaped moment by the interaction between a frozen relic and the intense energy of the sun. The solar wind does not blow uniformly. It fluctuates, gusts, changes direction subtly. This creates variations in the ion tail that can be quite dramatic. Sometimes the ion tail becomes kinked or broken. Sometimes it undergoes dramatic structural changes over the course of just a few hours. Dust tails can fragment and reform as the nucleus rotates and different regions of the surface become exposed to sunlight. What we observe from Earth or from spacecraft sent to investigate is a dynamic, ever-changing system. The comet is not a static object, but a process, a world slowly unveiling itself. The beauty of this anatomy lies in its impermanence. The nucleus may be ancient, but the coma and tails exist only in the presence of solar heat. As the comet recedes from the sun, as the nucleus cools, the outgassing slows, and the tails gradually fade. The magnificent structure dissolves. The dust continues to circle the sun, eventually dispersing into the interplanetary medium. The ions recombine with electrons and become neutral atoms once more, joining the thin wisps of gas that pervade the solar system. The comet's anatomy is thus a temporary revelation, a flowering that lasts only a few months, or at most a few years, before the comet retreats to the cold depths from which it came. Yet in those brief weeks or months, it tells us an intricate story about the nature of our solar system's infancy, about the processes that connect a frozen nucleus to the solar wind, about how matter and energy interact across the vast emptiness of space. For thousands of years, before telescopes existed, before the mathematics of gravity could explain their paths, comets arrived like visitors from beyond the world. They sparked something deeper than curiosity in the ancient mind. They sparked fear, wonder, and the impulse to weave meaning from the sky. Imagine standing in Babylon around the 8th century before the Common Era. The night is clear, the constellations wheel overhead in their familiar dance, and then, one evening, a new light appears, faint at first, then growing brighter and stranger, a ghostly smear stretching across the darkness. The Babylonian scribes and priests who watched the heavens would have noted this carefully. They kept meticulous records, these keepers of the sky. Clay tablets survive today, documenting comets observed over centuries, their positions and colors, and the length of their tails. But they did not see a simple wanderer of ice and dust. They saw omens, portents, messages from the realm of the gods. In the Babylonian worldview, the heavens were not distant and indifferent. They were alive with intention. Comets were divine signs, and they appeared when the gods wished to speak, often, unfortunately, to announce calamity. War, famine, the fall of a king. The comet was a warning written in light, a whisper from the immortal realm that human affairs below were being watched and judged, and so the priests would interpret, would consult, would warn the rulers. Was there a comet visible when this kingdom fell? Then perhaps another comet would precede the next upheaval. The connections seemed to fit so naturally into the shape of history. Now turn your gaze east, to ancient China, where comets held an equally profound place in the understanding of the cosmos. The Chinese astronomers were perhaps the most systematic observers in the ancient world. They kept records, extraordinary records, of comets spanning over 2,000 years. Some of these accounts are so detailed that modern astronomers can use them to trace the historical appearances of famous comets. But what is striking is that the Chinese too saw comets as messages, though their language for understanding them was different. In Chinese cosmology, the emperor was the bridge between heaven and earth. He carried the mandate of heaven, a sacred authority that could be withdrawn if he failed in his duties or if heaven grew displeased. And comets, in this framework, were heaven's way of expressing its displeasure. A comet in the sky meant something was wrong with the rule of the empire. It could indicate that the emperor was failing in his moral obligations, that natural disasters would follow, that the cosmic order itself was tilting out of balance. And yet there was also something more subtle here. The Chinese understood comets as celestial bureaucrats, as officials or messengers serving in heaven's vast administrative hierarchy. They had functions, they had meanings that could be read if you knew how to look. The difference in the shape and position of a comet mattered. A comet appearing in the east might foretell trouble for the eastern provinces. A comet with a tail pointing in a particular direction might carry a specific message to a specific region. This was not mere superstition, or rather, it was superstition that grew from genuine observation. The Chinese astronomers were watching carefully. They were seeing things. They were simply interpreting what they saw through the lens of their own cosmological framework. Move westward now, to ancient Greece and Rome, where comets carried yet another shade of meaning. The Greeks had a more philosophical bent, and they debated among themselves whether comets were truly celestial objects at all. Some philosophers, including Aristotle himself, believed that comets were merely phenomena in the upper atmosphere, not really part of the heavens at all, exhalations of the earth that ignited high above, then faded away. They were not immutable, eternal objects like the planets and stars. They were transient, impermanent, born and dying in the thick air above the world. And yet in the broader culture, in the minds of ordinary people, and even many educated ones, comets were still omens. They still carried meaning. When Julius Caesar was assassinated in 44 BCE, a bright comet appeared in the sky shortly after. Afterward, people remembered it. They spoke of it. It seemed fitting, in a way, that a cosmic disturbance would mark such an earthly one. The assassination of a leader, the disruption of the empire, these were reflected, echoed, predicted, or announced by the appearance of an unusual star. The comet became woven into the story of the event, a symbol of disorder, a sign that even the heavens recognized the gravity of what had occurred. What is remarkable is that across all these civilizations, Babylon, China, Greece, Rome, there is a common impulse. Whenever a comet appeared, it meant something. It was not random. It was not merely a natural object following laws we did not yet understand. It was a message, a warning, a sign, and perhaps this impulse, this hunger to find meaning in the unexpected, is very human. We are creatures who search for patterns, who connect dots, who want to believe that the universe is aware of us and communicating with us. The comets, of course, knew nothing of these interpretations. They moved through space, according to the same gravitational forces that would not be understood for another 1,000 years or more. They arrived on schedules set by physics, not by divine intention or bureaucratic assignment. And yet in those ancient nights, as people gazed upward and felt a mixture of awe and dread, they were not entirely wrong to sense something profound. They were sensing that these objects came from elsewhere, from the vast cold spaces beyond the Earth, from a region of the cosmos that was largely unknown. They were sensing, without the words or the science to express it, that they were being visited by something ancient, something that had traveled far, something that carried with it the mystery of deep space and deep time. Among all the wandering ice travelers of the outer solar system, one comet has earned a peculiar place in human memory. Its name is Halley, and it returns to our inner solar system not by accident, but with the regularity of a heartbeat, once every 75 or 76 years, a rhythm so predictable that it becomes almost a companion to human generations. To trace its visits across history is to hold in your mind a kind of temporal map, a thread of light connecting distant centuries through the eyes of those who watched it pass. The earliest human record we possess of this visitor comes from ancient Chinese astronomers, meticulous keepers of the sky, who understood that something meaningful moved among the stars. In the year 240, before the Common Era, they documented a bright, unexpected visitor whose tail stretched across the darkness like a celestial brushstroke. What they could not have known, of course, was that they were witnessing the same object that would return again and again, a cosmic pendulum swinging between the frozen reaches beyond Neptune and the inner warmth of the sun's domain. Centuries unfolded. In 1066, the comet appeared again, and this time its arrival was woven into the tapestry of human consequence. The biotapestry, that extraordinary medieval embroidery, captured its image, a reminder that this frozen wanderer had become entangled with human history and human anxiety. The appearance preceded the Norman conquest of England, and many who witnessed it wondered if the comet had announced something momentous to come. In that distant year, there was no way to know that what seemed like an omen was simply a body of ancient ice and dust, obeying the quiet laws of orbital mechanics, returning home as it always did. With each passing century, the sightings accumulated into a pattern that human intelligence could eventually perceive. In 1308, the comet came again. In 1408, in 1508, a man alive in that generation might glimpse it once, and if he lived long enough, might see it reappear when he had grown old, or might pass the memory of it to children who would live to see its return. Such a rhythm speaks to something profound in how we experience time. We are creatures who live for decades, not centuries. A human lifetime is brief against the vast chronology of the cosmos, and yet this particular comet offered a strange gift, a recurring appointment with wonder that could span generations. By the time the 17th century arrived, bringing with it the emergence of systematic observation, the pattern had become undeniable. Astronomers had begun to catalogue and compare the historical records, noting the intervals, feeling the gravitational certainty beneath the mystery. The comet appeared in 1602, then 1676. The interval held steady, beautiful in its precision, 3/4 of a century, again and again, as reliable as seasonal change yet far slower, a rhythm that operated on the scale of human lifespans rather than the turning of a single year. And this is where something remarkable happened, a moment when human understanding shifted from wonder toward knowledge. A mathematician and astronomer named Edmund Halley, himself born in the year the comet had appeared in 1656, studied these accumulated records with patient attention. He recognized that the comet of 1602, the comet of 1676, and the comet of 1532, and all the others, stretching backward through the centuries, were not different comets at all. They were one comet, one object, one ancient piece of the solar system, bound by the sun's gravity, orbiting in a vast ellipse that took it far beyond the planets and then back again, back across the inner solar system, its return timed and predictable, governed entirely by the immutable physics that had been revealed by Isaac Newton. It was a staggering realization. For the first time in human history, the distant and the celestial were shown to obey the same laws as the terrestrial. A frozen body hurtling through the vacuum would return exactly when the mathematics predicted. The comet had become an equation made manifest in light. Halley himself would not live to see the vindication of his prophecy. He died in 1742, confident in his calculations, but never seeing proof. Yet, when the comet blazed across the night sky in 1758, appearing within the year he had predicted, his name became linked forever with this returning visitor. The comet became Halley's comet, not because he discovered it, but because he understood it. He transformed it from an apparition into an orbit, from mystery into mechanism, and in doing so, he gave it a kind of immortality in human knowing. There is something deeply settling about this thought, something that speaks to a particular human longing. We live in a universe that often seems random and chaotic, where futures feel impossible to predict. And yet here is proof that across the seeming randomness of the heavens, there exists order, pattern, return. A comet follows its path, as surely as your own heartbeat follows its rhythm. It will come again, and the mathematics that governs its motion is the same mathematics that holds you gently in the sun's gravity right now, keeping you from spinning away into the darkness. The comet appeared in 1810, and the year before, the great eruption of Mount Tambora cast ash into the atmosphere and dimmed the sun. The comet appeared in 1861, and the world watched it cross skies transformed by the Industrial Revolution, observed through telescopes of unprecedented power. In 1910 it came, and aeroplanes had only just learned to fly. The comet remained indifferent to all of this human progress, all of this achievement and transformation. It moved as it had always moved, bound by the same force that had bound it for 4 billion years, returning home with the patience of something that experiences time in a scale almost incomprehensible to creatures like ourselves. In 1986, it appeared once more, and this time human ambition had reached far enough to send spacecraft out to meet it. The ice nucleus, the body of this ancient visitor, was finally seen with precision, and then the waiting began again, the quiet, patient waiting that characterizes all celestial mechanics. The comet moved away, receding into the darkness beyond the planetary orbits, toward the cold, slow spaces where it would coast for 75 years, unchanging, undisturbed, until once more the gravity of the sun would begin, gently and inexorably, to draw it home again. For many centuries, the question of what comets truly were remained shrouded in uncertainty and often in fear. The medieval scholars of Europe inherited a cosmos divided into two realms: the earthly sphere below the moon, home to change and decay, and the celestial realm above it, where all objects were thought to be eternal and unchanging. Comets, blazing across the night sky with such sudden, unpredictable brilliance, seemed to defy easy classification. Were they atmospheric phenomena, born and dying within the air surrounding our world, or did they belong to that pristine realm beyond? For centuries, the answer remained contentious, wrapped in philosophy rather than measurement. But slowly, almost imperceptibly, a shift began to take hold across Europe. The Renaissance brought with it a quiet hunger for direct observation, for measurement, for the kind of careful documentation that might replace speculation with certainty. Astronomers began to look upward, not with the eyes of mystics seeking omens, but with the eyes of natural philosophers asking precise, geometric questions. What was the comet's distance from the Earth? Did it move relative to the fixed stars in the way predicted by the old models? Could its position be triangulated, measured, pinned down to actual numbers? One figure emerged from this age of methodical stargazing, with particular clarity and consequence: Tycho Brahe, a Danish astronomer born in 1546, who would dedicate his life to measuring the heavens with an obsessive precision that bordered on monastic devotion. Tycho lost much of his nose in a duel over a mathematical dispute, a telling detail, perhaps, about the passions that burned in the breasts of Renaissance scholars, and he wore a metal replacement for the rest of his days, a quiet monument to the stakes of knowledge. He constructed an observatory on a remote Danish island called Uraniborg, the castle of the heavens, where he gathered instruments of unprecedented sophistication and accuracy. For decades, he watched the sky with meticulous care, recording positions, angles, measurements, building a vast archive of celestial data that would outlive him by generations. When the great comet of 1577 blazed suddenly into view, Tycho seized the opportunity with the focus of a man who had waited his whole life for such a moment. He observed it carefully, night after night, measuring its apparent position relative to nearby stars from different locations. What he discovered through geometric triangulation was revolutionary. The comet showed no parallax, or rather, it showed so little that it must lie far, far beyond the moon. This was the moment when the old medieval cosmos began to crack. If the comet orbited beyond that ancient celestial boundary, then it was not an atmospheric phenomenon of the earthly realm. It belonged to the heavens themselves. The distinction between the sublunary and superlunary worlds, which had structured all of medieval cosmology, began to blur. Other astronomers followed in Tycho's footsteps, adopting his methods of precise observation. Each comet that appeared, and in the decades following Tycho, several spectacular ones graced the sky, was subjected to this new rigorous scrutiny. The measurements accumulated, the certainties grew. Comets were not confined to Earth's envelope of air. They moved through the celestial realm itself. And this raised a new, tantalizing question. If comets inhabited the heavens, what were the laws that governed their motion? How did they obey the same rules, if they did, that governed the planets in their stately orbits? The cosmos was beginning to reveal itself as a place of order and pattern, waiting to be understood. But that understanding would require minds even greater than Tycho's, and a framework, gravity itself, that had not yet been invented. As the 17th century unfolded, Europe's astronomers and mathematicians found themselves in possession of something new and precious: reliable data. Tycho's decades of patient measurement had gifted them coordinates, angles, distances. The comets, once mere portents to be feared and interpreted, had become objects of mathematical study. Scholars could now ask not "what does this comet mean?" but rather "where is this comet, and why is it there?" The shift was subtle but profound, a movement from reading the cosmos as a text of hidden meanings to reading it as a book of hidden laws. By the end of the 17th century, something extraordinary was beginning to shift in how humans understood the heavens. For thousands of years, comets had belonged to the realm of wonder and dread, existing in a kind of cosmic uncertainty where no one quite knew what they were or where they came from. But now, in the quieted study rooms of England and across the learned institutions of Europe, mathematicians were beginning to ask a different question. What if the same force that held the moon in its orbit around the Earth, the same invisible pull that kept the planets circling the sun, also governed the movement of comets? What if these apparitions were not supernatural visitors at all, but rather travelers bound by mathematics as precise and orderly as a pendulum's swing? In 1684, an astronomer named Edmund Halley found himself in conversation with his friend Isaac Newton about the motion of the heavens. Newton had recently completed his revolutionary work on gravity and motion, and Halley was deeply curious about how this new understanding might apply to comets. The two men sat together, likely in the soft glow of candlelight, and Newton suggested something almost casually, that comets, like planets, must be traveling in elliptical orbits around the sun. If that were true, then a comet could return, over and over again, on a path that could be calculated and predicted. Halley became almost obsessed with this idea. He began to gather historical records of comet sightings, going back centuries into the dusty archives of astronomical observations. And as he studied the dates and positions of bright comets that had appeared throughout recorded history, a pattern began to emerge from the chaos. A comet had been seen in 1531, another had appeared in 1607, and another in 1682, just a few years before Halley was doing his research. The intervals between these sightings were roughly 75 years. Could they be the same comet, returning again and again on a reliable elliptical path? The notion was so profound, so utterly transformative, that it seemed almost impossible. For the first time in human history, a comet was not an omen, or a harbinger, or a mysterious celestial oddity. It was a member of the solar system, as much a part of the cosmic order as Jupiter or Mars, bound by gravity to follow a path that could be measured and anticipated. Halley made his prediction. The comet would return in 1758 or 59. He himself would not live to see it. He died in 1742, but he had made a gift to posterity. He had given future astronomers a date to watch for, a chance to prove that the heavens followed laws as certain as those on Earth. And so, as the middle of the 18th century approached, astronomers across Europe began to prepare. They set up their telescopes and waited with quiet anticipation. And then, in December of 1758, the comet appeared exactly where the mathematics had predicted it would be. The sky opened, and Halley's comet returned, vindicated his vision, and transformed forever how humanity understood the night sky. It was no longer enough to see the comet and wonder. Now we could see it, predict it, and know that it would come again and again on a schedule as reliable as the turning of the seasons. And this was perhaps one of the most profoundly settling realizations in the history of astronomy. The universe was not chaotic. It was not governed by caprice or divine whimsy. It was ordered. It followed rules, and those rules could be understood, written in equations, and used to foresee the future. A comet that had been feared in the time of Shakespeare, that had been interpreted as a sign of war or plague or the end of times, was revealed to be simply a traveler in space, following a path so predictable that a human mathematician could calculate where it would be dozens of years before it appeared. Newton's mathematics and Halley's patience had done something remarkable. They had tamed the comet, not by changing it, but by understanding it. And in doing so, they had offered humanity a profound comfort, the knowledge that even the most distant and seemingly alien objects in the night sky were not beyond comprehension. They were not beyond the reach of human reason. They could be studied, predicted, and understood. The comet fell into line with all the other celestial bodies, bound by gravity, following orbits as mathematically elegant as the curves of a spiral or the arc of a thrown stone. And this knowledge, this understanding that the heavens were governed by law rather than mystery, allowed human minds to rest just a little bit easier when they looked up at the darkness above. As the 19th century drew slowly onward, a remarkable shift began to unfold in how humanity could finally see these distant wanderers with clarity they had never before possessed. The invention of the photographic plate, that delicate glass coated with light-sensitive emulsion, suddenly offered something extraordinary, a permanent record of starlight itself. For the first time, astronomers could capture the actual image of a comet, preserve it, study it at leisure in ways that the human eye, no matter how keen or patient, could never quite manage. Where sketches had once been the only testimony to a comet's appearance, now the photograph stood as objective witness. The comet's tail could be measured with precision. The coma's brightness could be compared night after night. The subtle changes in structure as a comet approached the sun, drawn closer by gravity's steady pull, could finally be observed not through memory or hurried notation, but through the patient language of light itself. And yet, even as the photograph revealed the outer form of these celestial visitors with unprecedented detail, astronomers found themselves drawn to a deeper question. What were comets actually made of? What substances composed that ghostly nucleus hidden within the bright coma? What chemical elements blazed within that ethereal tail that sometimes stretched across the entire evening sky? Photography alone could not answer these mysteries. So in the later decades of the century, another transformative tool began to arrive in observatories around the world. Spectroscopy, the science of separating light into its component wavelengths, reading the invisible fingerprints that each chemical element leaves upon starlight, opened an entirely new window into the comet's nature. When starlight from a comet passed through a prism or diffraction grating, it revealed its secrets in the form of emission lines, those bright bands of color set against a darker background, like a barcode written in light. There was the crimson line of hydrogen, the green of diatomic carbon, the violet hints of cyanide. Yes, cyanide, that poisonous molecule that scientists found distributed throughout the coma, and yet which posed no threat whatsoever to Earth, so vast is the space between worlds. Each line told a story about the comet's composition, about the molecules that had been frozen in its nucleus for billions of years and now released as solar heat gently vaporized the surface. The spectroscope revealed that comets were not made of fire, as some had long imagined, but of ice and rock and organic chemistry, ancient chemistry, primordial chemistry, the preserved remains of the solar system's earliest moments. This understanding grew richer more complex, as the 19th century gave way to the 20th. Better telescopes, more sensitive photographic plates, increasingly sophisticated spectroscopes, all working in concert to paint a gradually clearer portrait of what a comet truly was. Astronomers in Europe and America and Japan observed that the tails of comets were not solid structures, but clouds of particles so sparse, so delicate, that you could see the stars shining through them. They noticed that the dust tail and the gas tail behaved differently in sunlight, streaming away in slightly different directions, pushed by different forces. The gas tail, they realized, was shaped by something invisible yet powerful, the solar wind, that continuous stream of charged particles flowing outward from the sun. The dust tail, being heavier and less responsive to magnetic and electrical forces, trailed somewhat behind, giving comets their characteristic curved or fan-like appearance. What emerges from this long century of patient observation is a portrait of remarkable intimacy. Not intimacy of closeness, you understand, but intimacy of understanding, of finally beginning to know these objects that had inspired awe and fear and wonder for millennia. The comet revealed itself, through the patient work of countless observers with their cameras and spectroscopes and careful measurements, to be a fragile thing, a relic, a messenger from the ancient past, carrying within its frozen form the very materials from which the solar system had coalesced. The ice held water, yes, but also frozen methane and carbon dioxide and ammonia. The dust contained silicates and carbon compounds, and perhaps most profoundly, organic molecules, the basic chemistry of life itself, preserved in a form so cold and so stable that it had remained essentially unchanged since the birth of the sun itself. There is something deeply restful in contemplating this slow revelation. No dramatic discovery happened all at once. Instead, decade by decade, image by image, spectrum by spectrum, the truth accumulated like snow, gentle and persistent. Astronomers did not shout in triumph at a single moment. Rather, they built their understanding patiently, collaboratively, across continents and languages and generations. The 19th and early 20th centuries saw comets transform, in the human mind, from supernatural portents into understandable objects of nature, still mysterious, still beautiful, but now knowable. And in that transition lay something quietly profound, the demonstration that mystery and understanding are not opposites, but companions. The more we knew about comets, the more wondrous they became. The 20th century drew to a close with humanity possessed of a new hunger, not to merely observe comets from the safety of Earth, but to reach out across the void and touch them. And in 1986, when Halley's Comet returned one more time to grace our inner solar system, 5 different spacecraft rose from 5 different nations, piloted by engineers and dreamers who had spent years plotting trajectories through the dark. The European Space Agency's Giotto was among them, named for the Renaissance painter who had witnessed Halley's passage centuries before and immortalized it in a fresco, unknowingly recording astronomical truth in tempera and gold leaf. Giotto would be the one to fly closest, to dare a dive into the very heart of the coma, that vast envelope of evaporated ice and dust swirling around the nucleus. On March 14, 1986, it hurtled past at a relative velocity of 68 kilometers per second, incomprehensibly fast, yet collecting images and data as it descended. The nucleus resolved itself in those final moments, a dark, potato-shaped object perhaps 10 kilometers long, rotating slowly, almost sedately, as if unperturbed by the spacecraft screaming past. What Giotto revealed was that a comet's heart is far smaller, far more modest than anyone had truly expected, and that realization brought with it a kind of calm, a settling sense that even these ancient wanderers are humble things. But the age of impact missions was only beginning. Decades would pass before another great ambition took flight, this time to deliberately strike a comet and observe the aftermath. Deep Impact, launched by NASA in 2005, carried both an orbiter and an impactor spacecraft. The plan was elegant, audacious, and executed with extraordinary precision. On July 4, 2005, the impactor detached itself from the orbiter and plunged directly into Comet 9P/Tempel 1 at a velocity of nearly 37,000 kilometers per hour. The collision ejected an enormous plume of material, water ice, dust, organic compounds, all illuminated by sunlight and observed from both the receding orbiter and telescopes on Earth. Scientists were astonished to find that the comet's interior was far more porous, far more loosely bound than had been predicted. It was like striking not solid rock, but a cosmic snowbank, crumbly and yielding, suggesting that these small bodies are held together not by any great internal strength, but by the gentlest of gravitational whispers. The dust cloud that erupted spoke of the comet's true nature, a soft accumulation of primordial material, barely more coherent than the solar nebula from which it formed. Yet perhaps no mission would come to touch the heart of human wonder quite like Rosetta and Philae. In 2014, after 10 years of pursuit through the solar system, the European Space Agency's Rosetta spacecraft finally caught up to Comet 67P/Churyumov-Gerasimenko, and rather than merely observing from a distance, it deployed a small lander named Philae to set down upon the comet's surface itself. This was not a collision but a meeting, the first time any human-made object had ever rested upon the body of a comet, had ever come to rest in that realm of ancient ice and dust. Philae's touch was gentle but precarious. The comet's gravitational pull is extraordinarily weak. Standing on its surface would feel less like standing and more like floating, anchored only by the faintest of downward tugs. The lander bounced after its initial contact, drifting upward like a feather released in a dream, before settling into a crevice on the comet's darkened slope. For the scientists watching from Earth, it was a moment of profound uncertainty, of holding breath across the immense distance, waiting to learn whether the lander would remain tethered or drift away into the void. But it held. Philae remained, and in those hours and days before its batteries faded, it transmitted back images and measurements that transformed our understanding of these ancient wanderers. What Rosetta revealed, orbiting Comet 67P for 2 full years, was a world of astonishing complexity. The comet's nucleus is a strange, bifurcated thing, 2 roughly spherical lobes connected by a narrow neck, as if 2 separate bodies had collided and become gently joined. Its surface is carved with cliffs and boulders, with deep pits and sinuous ridges. As the comet approached perihelion, growing warmer in the sun's embrace, its surface began to sublimate, jets of gas and dust erupting from cracks and fissures, streaming outward in patterns that shifted and changed from day to day. The spectrometers aboard Rosetta analyzed the composition of these outgassing materials and found them rich with organic compounds, carbon-based molecules that had slept undisturbed for billions of years, suddenly awakened by solar warmth. There was water ice, of course, ancient frozen water locked into the nucleus. There was carbon dioxide and carbon monoxide, methane and ammonia. These are the molecules of life, or the precursors to them, and here they were, being released from a body that had preserved them since the solar system's youth. The recordings that came back from Rosetta were themselves revelatory in a way that touched something deeper than mere scientific fascination. Acoustic instruments detected the sounds of the comet, the subtle creaking and shifting of its structure, the whisper of gas and dust being ejected into space. These were not the shrieking sounds one might imagine, but rather low, almost meditative murmurs, the ancient voice of a world awakening after eons of slumber in the cold. To hear a comet, To know that these objects are not lifeless, inert things, but active bodies undergoing profound transformation. This was to understand them in a way that no telescope observation could quite provide. They are not static fixtures of the sky, but breathing, changing, moving through their orbits like living things, slowly evolving and shifting across the millennia. The data that Rosetta gathered across its mission fundamentally altered our picture of what a comet truly is. A comet is not merely a chunk of rock and ice held together by mutual gravitation, but rather a loosely bound aggregate of material, a celestial dust ball held together by forces so subtle that a human standing on its surface would need to be tethered lest they drift away. It is a time capsule from the solar system's infancy, yet an active participant in its own evolution, releasing material into space and gradually diminishing with each passage near the sun. The nucleus is porous, riddled with voids and cavities, sometimes appearing almost pumice-like in its structure. The surface composition varies from region to region, some areas darker, some lighter, suggesting that different materials have concentrated in different places, or that the surface has been exposed to different histories of solar radiation and thermal cycling. And beneath the surface, the interior remains largely unexplored, preserved in its original state, awaiting some future mission that might drill or probe deeper. These modern missions transformed our relationship with comets from one of distant observation to something far more intimate. We have touched them, we have rested upon them, we have heard their voices as they sang through the vacuum of space, and in doing so, we have learned that there is no separation between the grandeur of these ancient wanderers and the profound simplicity of their nature. They are not mysterious or unknowable beings, but distant cousins of our own world, composed of the same elements, governed by the same physics, unfolding across the same timescale of cosmic evolution. And yet, for all the centuries of watching and wondering from Earth, the true voice of a comet remained utterly unknown until the moment a spacecraft finally drew close enough to listen. In November of 2014, the Rosetta orbiter, having chased Comet 67P through the dark spaces between worlds for nearly a decade, positioned itself to stay, to hover, to simply be in the presence of this ancient wanderer. What the scientists discovered in those early weeks was something that shifted how we understand comets, not as distant, silent objects of light, but as living, breathing, singing worlds. The nucleus of 67P, as Rosetta's cameras revealed it, was unlike anything anyone had quite imagined. Rather than a uniform snowball, it appeared as two lobes joined together, almost as if two separate bodies had gently merged eons ago, creating a shape that astronomers came to call a rubber duck, floating in the vacuum. And from this strange, tumbling world came sounds. Not sounds in any classical sense, for there is no air in space to carry vibrations, but signals, fluctuations in the plasma around the comet, a rhythm, the plasma instrument for magnetic field orientation and plasma experiment, shortened to PIMPLE, which itself contains a certain quietude, began detecting oscillations, a kind of gentle singing at frequencies just beyond human hearing. These weren't random pulses. They were coherent, structured, as if the comet were humming at a frequency of around 40 kilohertz, a whisper in the electromagnetic spectrum that only sensitive instruments could perceive. Imagine standing at the edge of an infinite silence and hearing, for the first time, that the silence itself has texture, that it breathes. But the sounds were only part of the story. What fascinated the Rosetta team most deeply was the outgassing, the way water vapor, carbon dioxide, and organic compounds, the volatiles, were slowly, steadily, almost rhythmically releasing from the comet's surface as it drew closer to the sun's warmth. During the day side of 67P's rotation, the sun's radiation would warm the ice just beneath the surface, and pressure would begin to build. Then, in a gentle cascade, the ice would sublimate, transforming directly from solid to vapor and burst free in delicate jets. These weren't violent explosions, they were more like exhalations, measured, patient, a comet, breathing out the accumulated secrets of 4.5 billion years. The measurements showed something remarkable. The outgassing wasn't constant. It followed the comet's own rotation, tied to the geometry of its lobes, sensitive to the precise angle of the sun's light. When Rosetta monitored the dust and gas emissions over weeks and months, patterns emerged. Activity would surge and fade. Some regions of the nucleus seemed far more active than others, as if the comet possessed what we might call personality, though such language strains against the boundaries of what we can truly know. One of the most meditative insights came from studying these jets more carefully. They didn't simply escape into space. The comet's own weak gravity, so faint that an astronaut could jump free of the surface, was still strong enough to pull some of the ejected material back. It would fall again, layer upon layer, creating new surface features even as the comet was losing mass. A kind of slow self-sculpting. The comet was literally reshaping itself through this gentle process of release and reaccretion, a cosmic version of breath and acceptance. And what was being released? Water, certainly. The spectrum showed that. But also carbon dioxide and carbon monoxide, organic compounds including methane and ethane, complex carbon-based molecules that, when analyzed, appeared to be older than Earth itself. These weren't new creations. They were messengers from the solar system's dawn, locked away in frozen form, now slowly being returned to the void from which they had emerged. There was something profoundly calming about observing this. The scientific detour into Comet 67P revealed a world that operated with no urgency, no haste. It had traveled across the inner solar system at speeds that seem fast only by planetary standards, yet on human timescales, the journey took decades. The outgassing happened molecule by molecule, jet by gentle jet. When you considered the vast spans involved, the comet had orbited once every 7.5 years and had been doing so for millions of years before Rosetta ever arrived. The emissions seemed not like loss, but like a kind of infinitely patient conversation with the sun. The Philae lander, Rosetta's small companion, managed to touch down on the comet's surface in November of that same year. And though it hopped unexpectedly due to the extraordinarily low gravity, bouncing and tumbling across the landscape for 2 hours before finally settling, the data it transmitted back carried another revelation. The surface was not uniform ice. It was porous, crumbly, in places almost friable, like ancient freezing soil. The ice here was not pure but mingled with dust and rock, creating a texture that suggested countless impacts over billions of years. And even at that moment of contact, Philae measured the outgassing continuing around it, as if the comet were responding to the gentle touch of human presence with its own quiet exhalation. What emerges from all of this is a sense of comets not as dead, sterile snowballs hurled through the void, but as dynamic, evolving bodies that slowly change as they journey through the solar system. The sounds Rosetta detected, the plasma oscillations, remain partially mysterious. The mechanisms that produce them are still being studied, still yielding surprises. But whether they arise from the interaction of charged particles with the comet's magnetic field, or from some other source yet to be fully understood, they remind us that the universe speaks in languages we have only recently learned to hear. And there is something deeply restful about this. The knowledge that a comet is not screaming into existence or collapsing into silence, but rather maintaining a gentle, constant conversation with the solar wind, releasing what it must release, holding what it holds, turning in its ancient orbit at a pace that asks nothing of us but patience. There exists within the deeper science of comets a question so ancient, so intimate, that it touches the very roots of what we are. And this question has only grown quieter, more profound, as our understanding has deepened. 4.5 billion years ago, when the solar system was still raw, still taking shape, the inner planets, including our Earth, were barren. Our world was a lifeless sphere of molten rock and gathering dust. And yet, we know now, with a certainty born from careful measurement and patient study, that Earth today is dominated by water. More than 70% of the surface swims in it, and beneath every living thing, in every cell and every strand of genetic material, water flows as an essential architecture. The question that hangs in that silence is deceptively simple. Where did all that water come from? For a long time, this mystery seemed impenetrable. The young sun's heat would have driven away volatile compounds, ice, vapor, the lighter molecules from the inner solar system. The heat was too intense, the radiation too fierce. Planets like Earth, forming in that scorching zone, should have been dry, desiccated. Yet we are not. And so our attention, over the past several decades, has gradually turned outward, toward the cold wanderers, toward the comets. Here is where the story becomes both scientifically grounded and beautifully speculative, which is to say, here is where science and wonder meet in genuine uncertainty. The theory, supported by increasingly refined measurements and isotopic analysis, suggests that comets, those ancient reservoirs of primordial ice, may have journeyed inward during the solar system's earliest, most turbulent centuries. Picture it, a comet, dislodged from the Kuiper belt or nudged from the Oort cloud, beginning its long fall toward the young sun. Over hundreds of thousands of years, perhaps even millions, these frozen wanderers could have rained down upon the still-forming planets. Some would have vaporized in the upper atmosphere. Others would have struck the surface directly, their impact releasing not only heat, but, crucially, depositing the water locked within their cores directly into the nascent world below. The numbers are, when you sit with them in the quiet hours, rather astonishing. Scientists estimate that even a relatively modest bombardment of comets, hundreds of thousands of them over a period of millions of years, could have delivered sufficient water to fill Earth's oceans many times over. And that calculation rests not on fantasy, but on measurements of water-ice abundance in the Kuiper belt and cometary observations. Yet there is a small, persistent puzzle within this theory. The isotopic signature of water in comets does not perfectly match that of Earth's oceans. Not all of it, at least. Some cometary water seems to bear a slightly different ratio of hydrogen isotopes than what we find in our seas. This discrepancy has led some researchers to propose that while comets certainly contributed, perhaps other sources, carbonaceous asteroids from farther out, or perhaps volatile compounds delivered through countless smaller impacts, may have played a role as well. The answer is not yet fully answered, and in that uncertainty lies an honest science. But water alone, however essential, is not life. Life requires something more. It requires complexity. It requires the molecular machinery of carbon-based chemistry. And here too, comets emerge from the darkness with an extraordinary gift. Within the structure of comets, locked in their dusty mantles and icy cores, are found organic molecules of staggering diversity, simple amino acids, hydrocarbons, nucleotide bases, the very building blocks from which DNA and RNA would one day be constructed. Compounds, in other words, that sit on the boundary between chemistry and biology. When comets strike a young planet, especially one still in flux, still being reshaped by impact and volcanic outgassing, they do not merely deliver water, they deliver the carbon-rich ingredients from which, given enough time and the right conditions, life itself might begin to stir. Is this proven? Not entirely. This remains, appropriately, one of the great open questions at the intersection of astronomy and biology. We know that the organic compounds exist in comets because we have measured them. We know that Earth needed water and organic compounds to give rise to life. We know that comets are abundant, ancient, and were likely abundant in the inner solar system during the period when Earth was still young and plastic. But the precise mechanisms, the exact pathways by which these cometary gifts became incorporated into the chemical and biochemical processes that would eventually yield the first living cells, remain to be fully understood. What we can say, with a certain quiet satisfaction, is that the atoms in your body have a lineage that stretches back to these frozen wanderers. The water in your blood, the carbon in your bones, the nitrogen in your proteins, all of it may carry, woven into its atomic history, a legacy written in ice and delivered across the empty gulf of space. The comets, in their slow and patient journeys, may have been, quite literally, the midwives of life itself. They traveled through the darkness for untold eons, silent and invisible, until at last they found a young world and gave it the seeds of everything that would come after. And yet, for all the journeys that have already taken place, for all the returns that Halley's Comet and countless others have made across the span of human history, the story of any given comet is far from finished. The future stretches before them, vast and patient, holding possibilities as ancient and inevitable as the deep cold from which they came. Consider, for a moment, the slow mathematics of a comet's eventual fate. Each time a comet swings close to the sun, it loses something. The heat and radiation strip away a thin layer of ice and dust from its nucleus. Molecules escape into space. The nucleus grows fractionally smaller, diminished by its own passage through the inner solar system. Over tens of thousands of years, over hundreds of thousands of years perhaps, this process continues, gradual and relentless. A comet that once measured miles across may, after countless returns, dwindle to something smaller, darker, less luminous. And somewhere along that endless sequence of orbits, eventually, a comet may simply scatter itself into fragments too small to detect, their remains dissolving into the general dust of the solar system, the material returning at last to something like the formless cloud from which all comets emerged. But not every comet follows this quiet path of gradual dissolution. Some, in a strange turn of cosmic fortune, encounter what physicists call a gravitational kick, a close approach to Jupiter or Saturn or another massive body that alters the comet's trajectory with sudden, irrevocable finality. And when that happens, a comet can be flung outward, away from the sun, sent spiraling into regions of space so vast and empty that the sun itself becomes merely one star among billions. The comet enters what we might think of as true interstellar exile, a journey that could stretch across millions of years, taking it toward regions of space that no human being could ever witness. And in that deep cold, away from the sun's warmth and radiation, the comet's nucleus would persist, unchanged, a frozen relic of the solar system's infancy, drifting through the dark between stars. It becomes, in a sense, a message in a bottle cast out into an ocean far larger than any ocean we know. What a strange thought, that somewhere in the universe there may be comets that originated in our own solar system, now traveling through the void toward other stars, other worlds, perhaps to eventually approach them as cautiously as they once approached our sun. There is a melancholy beauty in contemplating such a fate. A comet that has circled our star for millennia, that has been witnessed by humans across centuries and generations, could suddenly find itself in a trajectory that carries it beyond the sun's gravitational reach forever. The mathematics is elegant and inevitable. The forces that govern motion and gravity care nothing for the long history of observation, nothing for the human meaning we have ascribed to these wanderers. A comet is flung away, and its future lies in darkness and distance and the patient cold of interstellar space. Yet for most comets, the ending may come more softly. They will continue their slow fall and recovery, their approach and retreat, their gentle oscillation between the heat of the sun and the deep freeze of the outer solar system, for as long as the solar system itself remains intact. A comet 5 million years hence, or 50 million years hence, may still be returning to the inner solar system, still growing its tail as it draws near to the sun, still being observed, perhaps, by whatever conscious beings might inhabit this region of space by then. The universe is patient. Time moves at scales that make human lifespans seem like the blink of an eye. A comet, measured in thousands or millions of returns, is not remarkable on that time scale. It is merely part of the rhythm. But eventually, far in the future, the sun itself will change. It will swell. It will burn hotter. The planets will be altered. The gravitational arrangements that have held the solar system in its present form may shift in ways we can barely imagine. A comet that has survived for billions of years might find itself drawn inward, evaporating more rapidly, or ejected from the solar system entirely. Or the sun may enter its final phases, collapsing and cooling, and in that distant age, comets will still exist in the dark, their ice preserved, their slow dance continuing in a solar system transformed beyond recognition. What does it mean to think about the future of a comet? It is to embrace a kind of cosmic patience, a willingness to imagine timescales that dwarf the entire arc of human civilization. It is to recognize that these objects are not simply visitors, not simply curiosities for our brief moment of attention. They are ancient beings in the truest sense, older than mountains, older than oceans, likely to persist long after the sun has dimmed. They drift through the void with a kind of timeless quietude, untroubled by what lies ahead, already having journeyed farther through time and space than any conscious being ever will. In that thought, there is something profoundly restful. The comet asks nothing of us but to observe it for a moment. It carries on regardless, slow and certain, following the laws of motion and gravity, with an evenness that borders on the meditative. It will continue its work long after we are gone, leaving its light across the sky for whatever future generations might look up to watch. And so we arrive at the farthest reach of this journey, where a comet's luminous tail finally surrenders to the infinite dark. Picture that silhouette now, that graceful arc of dust and vapor unfurling across the black expanse, already beginning its slow dissolution into the very fabric of starlight from which it emerged. This tail, brilliant and streaming as it was during its passage near the sun, carries no weight, no permanence. The solar wind that once shaped it into that magnificent plume will, over the course of weeks and months, gently disperse each particle outward into the vastness, and the comet itself will become once more what it has always been at heart, a solitary wanderer, dark and nearly invisible, drifting through the silence between stars. There is something profoundly settling in this image, is there not? That gradual fading, that patient dissolution. The comet does not rage against this return to darkness. It does not resist. For billions of years, these objects have followed this same rhythm, a bright awakening near the sun, a time of radiance and visibility, and then an inevitable fade back into cold anonymity. They have learned, if we can speak of learning, a kind of surrender to the cycles that govern them. Consider how this mirrors something essential in the human experience, something we often overlook in our waking hours. Just as a comet spends most of its existence in the quiet void, traveling in solitude through immeasurable distances, so too do our bodies and minds know the value of stillness, of darkness, of time spent away from the glare and demands of the visible world. Sleep, in a way, is our own dissolution into the cosmic dark, not a loss, but a necessary return. A comet is most itself, not when it burns brightest, but when it rests in the patient cold, its icy nucleus intact, waiting. And we, too, become whole again in rest. The universe operates on timescales so vast that patience is not merely a virtue, it is the very fabric of existence. A comet waits thousands or millions of years between its visits to the inner solar system. The Oort cloud, that vast spherical shell of wandering ice at the edge of our solar neighborhood, exists in a state of perpetual, almost motionless calm. Nothing hurries there, nothing strains or reaches. The comets dwell in that ancient patience, and in doing so, they teach us something our faster, brighter moments tend to obscure, that rest is not the absence of purpose, but perhaps its deepest expression. As the comet's tail fades into the background constellation, becoming indistinguishable from the stars themselves, it leaves behind something remarkable. Every particle of dust it has shed, every molecule it has released during its approach to warmth, will continue on. Some will eventually reach toward worlds beyond, drifting for centuries through the interplanetary medium. Perhaps some will, in the incomprehensibly distant future, contribute to new formations, new beginnings. Nothing is truly lost. Everything returns, eventually, to rest. Your own rest tonight carries this same quality of continuation, of gentle transformation happening beneath the surface. While you drift towards sleep, your body is doing what the comet does during its long hibernation in the outer solar system. It is restoring, reorganizing, renewing itself through processes we are only beginning to fully understand. Your mind is processing, consolidating, finding patterns and meaning in the experiences of your waking hours, much as the universe itself slowly evolves and transforms across unimaginable spans of time. There is no competition between brightness and darkness, between motion and stillness, between the comet's fiery passage and its long sleep. Each is essential, each gives meaning to the other. The comet would have no tail without the sun's warmth, and without its long journeys through the cold, it would have no material left to shine. Similarly, your wakefulness gains its depth and color from the rest you allow yourself, and your rest gains its restorative power from the activities and engagements of your day. So let that image fade now, as we close this particular window into the cosmos. Watch the comet's luminous train dissolve gradually, peacefully, into the star field. Let it go completely into that vast, patient stillness. There is comfort in that dissolution, in that gentle fading into the dark. The comet will be there, somewhere out in the void, waiting. And you are here, resting now, knowing that in darkness and quiet, something profound and ancient and necessary is at work. The universe has been patient for billions of years. You can rest now, with that same patience, that same stillness, that same trust